Hello everyone, I'm Mighty, your hands-on practice assistant. In this session, we'll go through a CFD simulation together step by step and follow along with the practice example. Today's practice example is ESS air cooling analysis. In this tutorial, we will use a fan boundary condition to simulate the airflow and temperature distribution inside an energy storage system and evaluate how effectively the cooling fan removes the heat generated by the battery pack. What is an ESS? An ESS, or energy storage system, stores electrical energy and supplies it whenever it is needed. It can store electricity generated from renewable energy sources such as solar and wind power, as well as electricity from the power grid, and deliver it to industrial facilities, commercial buildings, or residential applications. During charging and discharging, battery cells continuously generate heat. Excessive temperatures can reduce battery performance, shorten its lifespan, and even create safety risks. For this reason, thermal management is a critical part of every ESS. One of the most common cooling methods is forced air cooling, using fans to remove heat from the battery pack. In this tutorial, we will use CFD to analyze the airflow inside an ESS and evaluate the cooling performance of its air cooling system. Why is air cooling important? Battery cells continuously generate heat during charging and discharging. If this heat is not removed effectively, the battery temperature rises, leading to reduced performance, shorter battery life, and even potential safety risks. An air cooling system uses fans to draw cool ambient air into the ESS enclosure and exhaust the heated air, helping maintain the battery pack within a safe operating temperature range. Effective air cooling improves battery performance and energy efficiency, extends battery life, and significantly reduces the risk of thermal runaway and other safety issues. For these reasons, a well-designed air cooling system is essential for ensuring the reliability, efficiency, and safety of an energy storage system. What is a fan boundary condition? A fan boundary condition represents the pressure rise generated by a fan without explicitly modeling the rotating fan blades. In reality, the pressure rise produced by a fan varies with the flow rate, and this relationship is described by a fan performance curve. In CFD, this performance curve is assigned to the fan location, allowing the solver to apply the appropriate pressure increase across the fan surface. First, the fan performance curve is defined, and then the fan boundary condition is applied to the fan face. During the simulation, the solver considers both the pressure rise generated by the fan and the resistance of the flow system to calculate the resulting airflow. The actual operating point is automatically determined at the intersection of the fan performance curve and the system resistance curve, which defines the operating flow rate and pressure rise. Because the fan geometry does not need to be modeled, this approach significantly reduces computational cost while providing accurate system-level airflow prediction. It is widely used in HVAC systems, ESS cooling, electronics cooling, automotive thermal management, and many other engineering applications. What is ESS air cooling analysis? ESS air cooling analysis is a CFD simulation used to predict airflow and temperature distribution inside an energy storage system. In this tutorial, we will use a fan boundary condition to simulate how cool ambient air enters the ESS enclosure, absorbs the heat generated by the battery modules, and is exhausted from the system. To perform the analysis, we define the fan performance curve, battery heat generation, ambient temperature, material properties, and the required boundary conditions. Based on these inputs, the CFD solver computes the airflow field and temperature distribution throughout the ESS. The simulation allows us to evaluate cooling performance, identify potential hotspots, and verify that the batteries operate within a safe temperature range. It also provides valuable insights for optimizing fan performance, airflow paths, and thermal management, ultimately improving battery performance, extending service life, and enhancing system safety. In this practice example, we will walk through the complete workflow of an ESS air cooling analysis step by step. Before proceeding with this practice, the contents are summarized and organized as follows. Let's briefly check the interpretation model and conditions. The overall model consists of two fans mounted on the left side, positioned at the front and rear of the enclosure. It is divided into solid and fluid domains. The solid domain consists of the battery modules and an aluminum frame, while the fluid domain is filled with air. The battery material properties are not selected from the material library. Instead, they will be defined manually using the values shown on the screen. First, launch NFX and click Open in the upper left corner to create a new project. Next, go to the Geometry tab, click Import, and load the CAD model. Once the model has been loaded, right-click in the workspace and select Hide All Guides to clear the view. Now, let's create the materials and properties. First, create the air material. Next, create the aluminum material from the material library. Then, create a new battery material, as shown on the screen. Enter the material name and define the mass density, specific heat, volumetric heat source, and thermal conductivity. After completing the material definitions, we'll proceed to create the corresponding 3D properties. Click 3D, move to the 3D CFD Analysis tab, and create the property for the material you just defined. Before generating the mesh, we will use the control seed function to define the mesh sizes in advance so that heat transfer and the airflow generated by the fan boundary condition can be captured properly. First, go to the Mesh tab and click Control Seed. In the solid domain, drag over only the tray region and select 120 edges. Set the mesh size to 0.01 meter and then click Apply. Next, drag over the fan housing and flow passage regions and select 215 edges. Set the mesh size to 0.01 meter and click Apply. This time, activate only the battery models, drag over them, and select 288 edges. Set the mesh size to 0.02 meter and click Apply. Finally, activate only the air domain model. Drag over the fan housing and flow passage regions and select 114 edges. Set the mesh size to 0.01 meter and this time click OK. Then shall we generate the 3D mesh? First, let's review the mesh generation strategy for each region. We will begin by generating the mesh for the battery and then proceed to generate the meshes for the air domain and the frame. Then, generate the 3D mesh as shown on the screen. Click the 3D tab, activate only the battery model, and configure the mesh settings as shown on the screen, including enabling the required checkboxes. After selecting all target regions for mesh generation, make sure that the properties have been correctly assigned. Then, click the arrow on the right and enable geometry proximity and avoid tetra with all boundary nodes to create a higher quality mesh. Set the mesh size to 0.02 meters for the battery region and 0.05 meters for the remaining domain. When generating the mesh, make sure to activate the Match Adjacent Faces and Merge Nodes checkboxes. These options are required to calculate fluid flow and heat transfer properly between each region, so please pay close attention to this step. For the initial mesh generation, it is not necessary to enable the Match Adjacent Face Mesh and Merge Nodes options. However, for all subsequent mesh generations, these two options must be enabled. Please make sure not to overlook this requirement. Now, mesh generation is complete. Let's make sure the mesh is generated well inside the model by using Clipping Plane function. Click Clipping Plane at the top of the model window, select the Y-axis, and then click Reverse. Now that mesh generation is complete, let's move on to setting the boundary conditions as shown on the screen. Follow along with the boundary condition setup process while watching the screen. Please also check whether the number of selected faces matches what is shown on the screen as you proceed step by step. First, click Fan Curve function under Define CFD function and create the fan performance curve as shown on the screen. Once you finish entering the values in the table on the left, the graph will be generated automatically. When the curve is complete, click OK. Next, under Inlet and Outlet, select Fan. Then select the two fan faces in the air domain. Assign the fan curve you just created and click OK. After that, select Pressure under Inlet and Outlet. Choose the air inlet face and click OK. Finally, select all remaining faces and apply the wall boundary condition. Be careful not to select the fan boundary faces or any other inlet faces while defining the pressure boundary condition. Finally, we will configure the monitoring settings. Select the two fan outlet faces and set up a monitor for the area average outlet temperature. Let's move on to creating and configuring the analysis case. If you right-click Analysis Case in the Analysis and Result tree on the left, you can see several predefined analysis types. From here, create a steady-state CFD, then click Edit. You will then see an analysis setup window. Now, let's configure the analysis settings as shown on the screen. Click Analysis Control and enable all three analysis modules. Next, click Initial Condition at the bottom, then select Field Definition. Set the initial temperature of both the fluid and solid domains to 25 degrees Celsius. Before running the simulation, save the NFX file to your preferred location. Then, right-click the analysis case you created and select Solve to start the simulation. This analysis may take some time to complete, so we will skip ahead and review the results. In the Analysis and Result tree on the left, you can review the results for each calculated step. First, let's review the temperature results. Click clipping plane and inspect the internal temperature distribution to verify that the heat generated by the batteries is being discharged effectively. Next, activate only the mesh of the air domain, select the velocity result, and review the velocity distribution. You can also visualize the streamlines by clicking Flow Path under the Fluid tools at the top. Finally, you can also view vector plots by disabling the contour display in the upper left corner of the Results tab and selecting Slice Plane Vector in Vector tab. Now let's review at the analysis results obtained from the simulation. By applying the fan boundary condition, the fan can be simulated conveniently without explicitly modeling its actual rotation. The temperature results show that the heat generated by the batteries is effectively carried out through the fans. This cooling behavior can also be confirmed from the velocity distribution and streamline results. While following along with today's practice, please make sure to remember these key points. How was today's lecture? Simulation may seem difficult at first, but if you follow the steps and practice hands-on, you can get started with confidence. With MIDASNFX, learn the fundamentals one step at a time and challenge yourself with a variety of simulation examples. Then, see you again in the next video. This has been Mighty, your hands-on practice assistant.